Creating a terrain from scratch is a technical challenge known as procedural generation. Scientists, video game developers, movie animators, geologists, and countless other professions use this technology every day. I think it's awesome, and today I'm going to show you how we get from a simple grid to a complex, lifelike terrain. Welcome to the beautiful world of procedural generation. I'll be using the Unity engine and will be coding in the language C#. In Unity, our terrain begins as a simple grid. We use game objects to represent each point on this grid. This code sets up the grid. These points will become our terrain. Now let's bring them to life. Through code, we are able to manipulate these grid points. We'll use mathematical functions for this. A simple yet effective choice is a sine wave, which we'll use to adjust the height of each point. I'm going to make a manipulator class that cross-references our terrain script. We can write methods here that will alter the grid points. We'll put the sine wave function here. In this code, we are iterating through each point on the grid and setting its y value equal to sine of x. I'm also going to increase the size of our grid. To better understand these concepts, we'll switch to a 2D orthographic view. This doesn't change the terrain, it just alters our perspective, making it easier to see how our functions affect the terrain. Back to our waves. The sine wave is defined by two properties: amplitude, which is the height of its peaks and valleys, and wavelength, the distance between the peaks. However, nature isn't this straightforward. To mirror its complexities, we'll add multiple wave functions together. I've altered the sine wave code. Now we have a list of numbers, called octave intensities. For each number in this list, we are adding another sine to the function, with half the intensity and half the amplitude as the previous one. So this is what it looks like. It's looking more natural, but our sine wave lacks randomness. It's still too orderly and systematic. Nature is inherently more chaotic. Enter Perlin noise. Perlin noise is a function. It takes an input, say the x-coordinate, and outputs a smooth, random number. It gives us patterns like this, which is distinct from sheer randomness, which you would get from a noise function or a hash function. You might be wondering how this function works, and it's surprisingly not too complicated and was a fun challenge to try and personally implement, but that's not what I'm here to talk about. And luckily for me, this function is accessible under the MathF class, which is included in the Unity engine. Anyways, when I switch the sine wave out with Perlin noise, this is what it looks like. Pretty cool. Let's up this from 2 dimensions to 3 dimensions by simply passing the z position value into the Perlin noise function instead of 0. I've also gone ahead and changed the terrain script to now render a basic material instead of rendering points. Now we've got some somewhat realistic terrain. At this point, I'm going to define a few other methods within the terrain manipulator script. Here's another wave function. This is a piecewise function that gives the appearance of repeating bumps. I've modeled it in the code and layered it the same way we did with the Perlin noise. This is what it looks like. I like how it's starting to look like a fractal. If I kept adding more and more layers indefinitely, I would end up with a very cool 3D fractal. The grid points that make up the terrain that you're looking at now have been ran through the Perlin noise function and had their values multiplied by the piecewise function. This results in a nice variety of fields and mountains. Here's another method, this one for simulating erosion. It iterates through all the points in the grid and sets its y position equal to the average height of all nearby points. We have variables for the radius size and strength. Before I move on, I'd like to talk about an algorithm that I didn't end up using. That's the diamond square algorithm. This is a common sequence often used to generate terrain. I implemented this in 2021 in a terrain generator, which can be found on my website, tylar.io. I'm not going to get into the algorithm, but I recommend looking into the topic if any of this sounds interesting. Okay, and lastly, here's a method that shapes our terrain into an island by lowering any points beyond a certain distance away from the middle. I'm pretty happy with how this is looking, and I'll improve it later, but for now, I think it's a good time to move on to shading. Okay, so a little bit about shading. I'm still new to it, and this is the first time I've ever worked with it, but here's my understanding. So unlike typical C# scripts that run on the CPU, shaders are programs that run on the GPU, meaning they execute much faster, but they don't have access to all the same data as normal classes. Surface shaders, which are the scripts I'll be writing, are used to handle lighting and shadowing on material of 3D objects. The main thing we can control are albedo, which is color, smoothness, which is a number between 0 and 1, and metallic, also a number between 0 and 1. And with these, we can come up with a pretty detailed material. We're given this method, surf, which is where we define the surface of the material at any given point. We have access to input information, such as position. We can also define the surface output. We give it values for albedo, smoothness, and metallic. Here I'm defining two types of materials, one for sand and one for grass. I've used .lerp to interpolate the two materials based on their height. While the program is running, we can change these variables within the material. I also went into the scene editor and added some water. Next up, I'm using Photoshop's generative AI tool to turn this Perlin noise image into a seamless, repeatable background that I can texture my terrain with. Once I have my image, I'll create a sampler 2D variable that references it. In the shader script, I'll have my image be added to the albedo at different scales. There are currently 3 different sized Perlin noises being added. If the point is below our lower bound variable, I'll add extra small Perlin noise to make it look like sand. So no matter what scale we're viewing the terrain at, it has a very natural texture. To enhance the mountainous and cliff-like features, I'm planning to assign a rockier texture to the steeper areas. This requires calculating the derivative at each point, for which I'll feed the grid height points from our terrain script into a new variable, vertex data text. I'm introducing a function named derivative that estimates the slope using adjacent points. Additionally, I developed 2 distinct materials and linked them to the derivatives in the surf function. Each material interacts uniquely due to their processing through different functions. For areas with high derivatives, I've added a layer of extra Perlin noise to create a more realistic rocky texture. Ah, yes! This is looking great! I'm so happy with how the rocks turned out. I love the separation between the rocks and the surrounding dirt. This cube is 6 feet tall, and the world's area is 1,500 grid points squared. Okay, this has been a lot of fun. I plan on turning this into some sort of game, but it is 3 a.m., 3:25 a.m., and I've been editing this video for too long. Thank you for watching, and you can download and experiment with the project in the description.